Our topic is about semiconductor diodes. Now that both P-type and N-type are available, we can construct our first solid-state device, the semiconductor diodes. Let's have some review of our topic last week. P-type semiconductor material has significant number of holes, which are the majority carrier and very few number of free electrons, which are the minority carrier. At the right figure, a boron atom doped into a silicon crystal. Boron is a trivalent atom. It produces holes, and adding more trivalent atoms produces more holes. Because of boron, trivalent are acceptor atom. It produces acceptor ions, and acceptor ions are negative ions. Why? Because they accept electrons, meaning mas marami yung electrons nila. To summarize, this p-type material, its majority carrier is holes, minority carrier is free electrons, and ang mga ions niya ay negative ions. How about N-type material? N-type semiconductor has significant number of free electrons and very little number of holes. The holes are also generated during electron-hole pairs. At the right side, antimony impurity doped to a silicon crystal. Antimony is a pentavalent atom. A pentavalent atom are donor atoms. It produces donor ions. And it is a positive ions. Why? Because nag-give up sila ng electrons. Meaning, mas marami na yung proton niya kaysa sa electrons. To summarize, the N-type material, majority carrier are free electrons, minority carrier are holes, and ang mga ions ay positive ions. Ngayong alam na natin ang two type of material, we can construct now a simple PN junction. Kapag pinag-combine natin ang P-type and N-type material, makakabuo tayo ng diode. Again, the majority carrier of P-type are holes and the N-type are free electrons. The ions at P-type are negative ions and the ions at N-type are positive ions. These ions, tandaan natin, it remains immobile in nature until bias is applied. What is bias or biasing? Biasing is the application of voltage across diodes terminal. Terminals of diodes are anode and cathode. Yung P-type material, siya yung anode, and yung N-type material, siya yung cathode. Let us first discuss how depletion region is formed. Once na kinombine natin ang P-type and N-type material, makakabuo sila ng junction. At ito yung junction. Or what we called PN junction. The electrons from the N-type region recombines sa holes ng P-type region. This process is called recombination. Recombination, again, is the process where electron drops into an empty state represented by hole. During recombination, these electron-hole pairs, yan, is being created. At kapag nag-combine tong electron-hole pairs, it disappear because it was converted to energy. And as the electrons from N-type recombine with the P-type, with the holes sa P-type region, depletion region gets wider. Gaya nga ng sinabi ko kanina, every time na magkakaroon ng electron-hole pairs, magdi-disappear yung electron-hole pairs dahil mako-convert siya sa energy. Dahil lumalaki na lumalaki yung depletion region dito, the electrons from N-type region, hindi na siya makaka-enter dahil sa depletion region. Depletion region is the junction where neither electrons nor holes exist. At dahil ang mga ions are immobile, it will remain at the depletion region. The ions at the depletion region creates an electric field known as barrier potential. Diode barrier potential is 0.7 volts for silicon and 0.3 volts for germanium. It requires threshold voltage equals to the barrier potential to switch the diodes at on condition. Later on, we will discuss about that. Now, we'll discuss about forward bias condition of a diode. Dito sa forward bias condition, the diode act as an on switch. For the diode to turn on, kailangan positive terminal ang nakakonect sa anode and negative terminal ang nakakonect sa cathode. Diode have threshold voltage or the required voltage for the majority carrier to flow. Silicon requires 0.7 volts and germanium diode requires 0.3 volts while gallium arsenide requires 1.2 volts. The application of forward bias voltage will pressure. Pinapaliit niya yung depletion region. Dahil pinipressure niya yung mga electrons sa N-type material and holes sa P-type material to recombine near the boundary and reduce the depletion region. Reducing depletion region allows heavy flow of current across the junction. As the applied bias increases, the depletion region will continue to reduce. At kapag na-reach na o above na sa threshold voltage, in this condition, ang diode mo ay naka-switch on. Now on reverse bias condition. The diode act as an open switch. Sa reverse bias, positive terminal is connected sa cathode and negative terminal is connected sa anode. Dahil opposite terminals, large number of free electrons sa N-type will be attracted sa positive terminal, kaya mas lalong lumalaki ang depletion region. The widening of the depletion region will establish great barrier for the majority carriers to overcome. So kaya siya open. When diode is reverse bias, it allows very small current, mga nasa microampere, to pass through it. Somewhat, yun nga, microamperes. The current is due to the movement of minority carrier. The current that exists under reverse bias condition is called reverse saturation current or what we call leakage current. So, yung minority carrier flow na napakaliit, yan ay leakage current. Diode has a reverse bias parameter known as breakdown voltage. Breakdown voltage is the maximum voltage of the diode can handle when reverse bias. It is also called peak inverse voltage. If this voltage exceeded, the diode may be destroyed. Okay, let's discuss the characteristic curve of a diode during forward bias condition. At x-axis, you will see forward voltage. It is also termed as cut-in voltage or threshold voltage. It is the required voltage in order to produce forward current or to make the diode conducts. The cut-in voltage for silicon is 0.7, while the cut-in voltage for germanium is 0.3 volts. At y-axis, you will see forward current. It is the magnitude of the current the diode can handle without burning when forward bias. This one is the characteristic curve of a diode during reverse bias condition. At x-axis, you will see reverse voltage. And this is the applied voltage during reverse bias condition. At y-axis, you will see reverse current, the electric current which is carried by the minority charge carrier. During reverse bias condition, the diode may experience breakdown voltage when the diode reaches the maximum reverse voltage before the current surges. This may cause damage to diodes. Another is the reverse saturation current. It is the maximum level of reverse current even if the voltage increases. Its unit of measurement is somewhat in microamperes. Next is the Shockley's equation. Shockley diode equation is a mathematical model of the forward and reverse bias characteristic of a diode. To solve for the diode current, see the formula in the slides, where IS is the reverse saturation current, VD is the voltage drop across the diode, N is the ideality factor, equals to 1, palagi yan, unless stated sa problem. VT is the thermal voltage. How to compute for the thermal voltage? Take note of this formula, where K is the Boltzmann constant, equal to 1.38 times 10 raised to negative 23 joules per Kelvin. And temperature in Kelvin, or the absolute temperature in Kelvin, to compute given that temperature in degrees Celsius, the formula is 273 plus the temperature in degrees Celsius. And Q is the magnitude of electronic charge, equals to 1.6 times 10 raised to negative 19 coulomb. Okay, let us solve sample problem. At the temperature of 27 degrees Celsius, determine the thermal voltage and diode current at reverse saturation current equals to 10 picoampere of a silicon diode. We first convert Celsius to Kelvin by adding 273 to degrees Celsius, and we will get 300 Kelvin. Next, transfer it to the equation of thermal voltage, where K is equal to 1.38 times 10 raised to negative 23 joules per Kelvin, and Q is equal to 1.6 times 10 raised to negative 19 coulomb. So we will get an answer of 25.875 millivolts. To compute for diode current, we'll use a voltage drop across the diode equals, dahil silicon diode yung gamit natin, we know that the voltage drop across silicon diode kapag naka-on ay 0.7 volts. And the reverse saturation current is 10 picoampere, and N is equal to 1 as our ideality factor. Transpose it to the Shockley's equation. We'll get 6.07 ampere. Okay, at voltage drop is equal to 0.7 volts. Okay, let us compute the diode current at voltage drop is equal to 0.1 volts to 0.6 volts and so on. So, yung current natin sa 0.1 volts is 0.47 nanoampere, and sa 0.2 volts is 23.25 nanoampere. Kung mapapansin nyo, pataas ng pataas yung reading ng current. 1.12 microampere sumunod, 54.11 microampere, hanggang naging 2.61 milliampere, and 0.6 volts is 125.86 milliampere. So, habang pataas ng pataas yung applied forward voltage, pataas ng pataas yung forward current natin. And kapag na-reach na nga yung 0.7 volts, makikita natin yung diode current ay pumalo ng 6.07 ampere. Meaning, naka-on na yung ating diode. At kapag nilagay natin yan in a graph, in a characteristic curve form, makaka-form tayo ng graph ng characteristic curve ng diode. Okay. There are three different resistance level of a diode depending on the type of applied voltage or signal. First is the DC or static resistance. So, ang applied voltage natin dito ay naka-DC. So, it is the forward resistance of the diode in DC circuit analysis. Tandaan ang formula. Diode resistance is equal to diode voltage over diode current. And, for example, determine the DC resistance level for the diode at diode current is equal to 2 milliampere, diode current is equal to 20 milliampere, and diode voltage is equal to negative 10 volts. Okay, simulan natin sa pinakauna. At diode current is equal to 2 milliampere. Check natin dito. So, ito ang 2 milliampere. So, ang diode voltage natin is 0.5 volts. Kaya 0.5 volts ang nakalagay dyan. So, diode resistance is equal to 0.5 volts over 2 milliampere is equal to 250 ohms. So, parang ano lang yan, Ohm's law. And then next, at diode current is equal to 20 milliampere. So, ang diode voltage natin o voltage across the diode is 0.8 volts. So, ang makukompute nating diode resistance is 40 ohms. How about diode across the voltage is negative 10 volts? So, ito yan. So, ang current natin is negative 1 microampere. So, ang diode resistance natin is negative 10 volts over negative 1 microampere. So, makukuha nating resistance value ng diode is 10 mega ohms. Another level of diode resistance is AC or dynamic resistance. Dito naman, this is the forward resistance of the diode in AC circuit analysis. For small signal analysis lang ito. Okay, diode resistance at AC is equal to ideality factor times 26 millivolts over diode current. Yung 26 millivolts, yan ay ginagamit na nating constant value ng thermal voltage ng diode. Where N is equal to 1 for above knee of curve and N is equal to 2 for on or below knee of curve. Pag sinabi nating knee of curve, kung may makikita kayong graph ng characteristic curve ng diode, sa curve doon na nag-on ang diode. So, pag below sa curve, sa knee of curve, ang nilalagay nating ideality factor ay 2. Mamaya, mag-solve tayo ng sample problem about this. But there is another AC resistance which is called average AC resistance. It is the forward resistance of the diode when in AC circuit analysis. It is for large signal analysis. Kasi, point to point na tayo. Kung baga, sa line, kahit gaanong line na yan, kahit gaanong kahaba, magpo-point to point lang ako, change in voltage drop across the diode sa point na yon and change in current sa point na yon, ipagma-minus ko lang. Okay? Change of voltage and change of current. Okay, let's try to solve an example problem. Okay, determine the dynamic resistance at diode current is equal to 2 milliampere. So, diode resistance is equal to ideality factor times thermal voltage over diode current. Dahil ang thermal voltage na gagamitin natin palagi is 26 millivolts and yung ID natin, yung diode current natin is given 2 milliampere. What is the ideality factor na gagamitin natin. Check natin, ito ang 2 milliampere. So, ito yung knee of curve. Dahil siya ay on or below the knee of curve, ang ideality factor na gagamitin natin ay 2. Pero kung ito ay nandito, above the knee of curve, ang ideality factor na gagamitin natin ay 1. Okay, so dahil below the curve or on the curve, 2 ang gagamitin natin. To get the diode resistance or the dynamic resistance, 2 times 26 millivolts over 2 milliampere is equal to 26 ohms. And next is determine the average AC resistance at diode current is equal to 2 milliampere. For diode current is equal to 2 milliampere, the tangent line was drawn. So, mapapansin nyo itong tangent line na ito. And a swing of 2 milliampere. Okay. Above and below the diode current. So, 2 milliampere below the diode current and 2 milliampere above the diode current, which is 0 and 4. So, pwede tayong mag-assume ng any value of swing. At diode current is equal to 4 milliampere, the diode voltage is 0.76. Okay, this is just an assumption. And for diode current is equal to 0 milliampere, makukuha nating voltage across the diode ay 0.65. So, ang average AC resistance again is the change in voltage across the diode and change in current or change in diode current. So, let's compute 0.76 minus 0.65 over 4 milliampere minus 0 milliampere. Ang makukuha natin is 27.5 ohms. Kung mapapansin natin, sa average AC resistance, ang nakuha natin is 27.5 ohms. Pero dito sa dynamic resistance, ang nakuha natin is 26 ohms. Ang difference ng dalawa na yan, 27.5 minus 26 ohms, tinatawag natin yung contact resistance. Contact resistance ng diode. Okay. So, ganun lang mag-compute ng iba-ibang resistance level ng diode. Okay, let's go naman sa equivalent circuit. So, madali lang ito. Pag sabi nating ideal model, it's either open switch or closed switch. Nire-represent lang siya ng switch pag ideal diode. Pag simplified model, combination siya ng battery and ideal diode. So, ganun natin nire-represent ang iba-ibang equivalent circuit ng diode. At kapag piecewise linear equivalent model, combination siya ng battery, ideal diode, and a resistor. So, yan lang yung pinagkaiba-iba ng tatlong equivalent circuit. Pero ang common na ginagamit natin dito, ideally, is yung ideal diode models. Okay, so yun lang yung topic natin for this day. Thank you for listening and see you on our next class.